All right, so let's continue. We're going to finish chapter 5. We're in 1.5, geometric interpretations of parameters of a linear function. So, kindly consider the following. Okay. What if I say I give you the population of 3 towns? PA, PB, PC, and PD. Okay. So here's PA, here's PB, here's PC, and here's PD for town A, B, C, and D. All right, the population of each. All right, now the population, as I said, with time t in years, the populations of 4 towns are given as follows. All right, so town A's population varies over time this way. 20,000 plus 1,600 t. Okay? Population of town B varies this way. 50,000 minus 300 t. The population of town C varies this way. 650 t plus 45,000. And the population of town D goes this way. 15,000 times 1.07 to the t. All right. Question 1. Which of these functions are linear and which of these are not? Any ideas? Are they all linear? Are there none of them linear? Is there all except for D? D is not linear. D is exponential. We'll get into exponential growth and decay eventually, but that's an exponential growth model. If you're taking powers of 1.07, something bigger than 1. If you take all right, let's put it this way. What is 2 squared? 4. What is 2 cubed? 8. What is 2 to the 4th? 16. If you take bigger exponents of a number bigger than 2, it gets bigger and bigger and bigger, right? But is that always true for any number? What is 1/2 squared? 1/4. It's getting smaller. What's 1/2 cubed? 1/8. It's getting smaller, right? So 1.07 is bigger than 1. When you square it, when you cube it, when you fourth it, is it getting bigger or is it getting smaller? 1.07 squared, is it bigger than 1.07? Right? 1.07 cubed, is it bigger than 1.07 squared? Right? It is. So that's an example of exponential growth. Okay. So that population is growing exponentially. The other 3 populations are growing linearly. What does that mean? Well, can you isolate the B in each of the populations of A, B, and C? What's B for population A? I'm talking about y equals mx plus b. 20,000. What does that represent? The y-intercept. Okay. More concretely, in the terms of the town, the initial population of t equals 0. Whatever t equals 0 means, t equals 0 could be 1980 or something, and t is in years. T equals 0 could be the year 2000, and t is in years, right? Whatever it is. So the initial population is 20,000. What's the initial population of town B? 50,000? Okay. What's the initial population of town C? 45,000. What's the initial population of town D? What if you plug in t equals 0? What's something to the 0? 1. And 1 times 15,000 is 50,000. So we know the initial population for town A is 20,000. The initial population of town B is 50,000. The initial population of town C is 45,000 because that's the y-intercept. And the initial population of town D is 15,000 because that's what you get when you plug in t equals 0 years. Okay. All right, what's the 1,600 in town A mean? Slope. Now remember, the slope is delta y over delta x. But in this case, it's not y and x. What is it? P and t. So it's delta p over delta t. And p is in what units? People. And t is in what units? Years. Okay. So that's 1,600 people per year. Now, is that a population increasing or decreasing? Increasing, because it's a positive slope, right? What about the slope in town B? Is it positive or negative? Negative. So the population is decreasing. What is it? Negative 300 what's? People per year. We're losing 300 people a year, okay? What's the slope in town C? 650, and it means we're gaining 650 people per year. Perfect, that's it. That's what they're talking about, that's what they mean about the parameters of a linear function. What does the B mean? What does the M mean in terms of the context of the word problem, of the real world problem? Okay? That's what they want to know. All right. How would you want to graph them? How would you graph these? What do they look like? Let's go to Ziggy. By the way, for the uninitiated, Ziggy is my nickname for the T83. That's you. You're the uninitiated. You didn't hear this yesterday, right? No. See, I'm picking on you all day. All right. So how do you graph this? Well, again, you know that A, B, and C look like lines, but D doesn't look like a line, does it? Let's see. Let's graph this. Y, turn it on. Go to Y equals. Everyone should have a T83 to follow along. A real T83 in your hand, right? Or 84. That's fine. All right, so let's change my Y equals here. All right, so 20,000. This is not in MX plus B form. It's backwards, but you know where the B is, right? 20,000 plus 1,600 T. All right, let's start with that. Now, in function mode on your calculator, you're stuck with X for input, not T. That's all. Now, what's a good window for this? Since you know the y-intercept is 20,000, and the slope is positive, you have to have at least 20,000 and more, right? So let's set up a window. Can you have negative time? Well, you can, but we're starting at t equals 0, right? All right, are we going to go to 600 years? I don't know. Let's how about, I don't know, maybe 10 years with a scale of 1. So these x's are really the t, okay? All right, what's a good window for y? Are you going to have negative people? Well, yes, some people are negative. But we'll start with 0 and go up to, well, how much? It has to be at least 20,000, right? Right, because it starts at 20,000 and goes up. So I don't know, I'm going to guess 100,000. And if I'm going by 100,000, how about a scale of 10,000? So you can see the tick mark every 10,000 on the y-axis and the tick mark every 1 year on the x-axis. Let's graph that. It's not growing very fast. Okay. In fact, none of these are growing very fast. 1,600 is the most, right? So maybe that 100,000 is a bit much. But all right, whatever. Let's graph this one. Can I graph this one in that window? What's the y-intercept again for B? 50,000. 50,000 is right here, right? And then it's decreasing. All right, so this is probably a good window to include the 50,000. Let's do that. Let's make town B equal to y2. 50,000 minus 300t. And as you said, this should be a decreasing function. And it is. Not very fast, but it is. Okay. And how about C? Let's make that y3. 650x instead of t, because that's how the calculator works, plus 45,000, a little bit lower than the 50,000, and that's increasing, and there you go. Okay. But now how about D? That's not a line, we said, right? Let's take a look at D. 15,000 times 1.07 to the, I'm going to use x again in function mode. And in this window, it doesn't look exponential. It almost looks linear. But there is a little bit of concavity here. There's a little curvature going on. It might be more obvious if I make the window a little bit bigger. Maybe 100 years. How about 100 years? 100 years from year 0 to year 100 in tick marks of 10. Let's see what that looks like. So there's town A, town B, town C, and then the exponential growth. There it is. You see how it's curving? Right? It's not a line. Right? Okay. So we're correct in our interpretation of the parameters of these functions, linear or not. That's what this section is about. Interpreting the numbers, the 650, the 1,600, the 50,000, the 15,000. What does it mean, right? Okay. Alrighty. All right, let me ask another question. When is the population of, let's see. Let me turn off, I'm going to turn off this one and this one. Notice it's still there if I need it, but I turned it off. Put the cursor there with your Nintendo keys and hit enter to turn it off so it won't graph. So I'm only graphing towns B and C. Here they are. What's the significance of that point of intersection? What does that mean? What does that point of intersection mean? What's true about where they intersect? They have the same point, x and y, on each line, right? All right, so isn't that where they have the same, if I figured out the x value there, that's time, and I figured out the y value there, that's the population, right? So that's when they have the same, at what time, what year do they have the same population? So how do you figure that out? Can you figure out that point? How do you know where they intersect? All right, let's take a look at that. Town B and Town C, right? Okay, let me get back over here. All right, so here's Town B. Town B was, the population is 50,000 minus 300T. And Town C was 650, well, P equals 650T plus 45,000. How do I find out when they have the same population and what that population is? How do I find the point of intersection T comma P where they meet? You know how to do this algebraically. How do you find points of intersection? At that point of intersection, they have the same population, right? So if the populations are equal, set them equal to each other and solve for T. Okay. So let's see, 50,000 minus 300T equals 650T plus 45,000. So how do you solve for T algebraically? Well, so what do you want to do? Add or subtract what? Add 300T? Okay. Add 300T to 650T and you get? 950T? Okay, so that's what I'm going to say. I'm going to get 50,000 left over here equals 950T plus 45,000. Remember, my aim is to get T alone. What else do you want to do? Do minus 45,000 from 50,000. What are you left with? 5,000. And one more step. Divide by 950. So T is 5,000 divided by 950. Ugh. Wow, I don't like the bottom of this tablet. It messes everything up. Divided by 950, which doesn't go in nice and even, but, well, if I divide it by 1,000, what would it be? 5,000 divided by 1,000 is 5. I'm dividing by less than 1,000, just a little. So the answer would be a little bit more than 5, right? All right, so let's go to Ziggy and ask Ziggy what 5,000 over 950 is. You could do this by hand, I guess, long division, but why? And that, remember, this is a fraction, 5,000 over 950, so this is probably some kind of a repeating decimal. If you get wacky decimals like this on a test or something, you can round it off to 3 places. So 5.236 years. Remember that this is in years, right? 5.236 years, okay. So it's a little bit more than 5 years. 5.236 years. Don't forget units in the answer when there's units in the question. Huh? 263, sorry. All great mathematicians are dyslexic. And not that I'm a great mathematician, but I am dyslexic. So 263? 263? Yeah? Okay. By the way, notice, exactly equal to 5,000 over 950. Approximately equal to 5.263. The dot on top of the equal sign, that means approximately equal, not exact. I round it off. Okay? So whenever you round off, do that. Don't write exactly equal because it ain't. Does it make sense? Is it okay? Okay. All right, now that's how you do it algebraically. But did you have to do any of that? No. How do you do that right here on the graph screen? Do you know how to get a point of intersection right on the calculator? Yeah. Super trace. Yeah, second trace. I call it super trace, which is calc, right? So go to second trace, which is the yellow calc key, and go to intersect. And since there's only 2 curves here, I don't care who's the first curve or second curve, just hit enter, enter, and I don't have to guess, enter. And we get 5.263, whatever again, right? But what else do we get? We get the population at that time. So the question was really twofold. When do they have the same population after 5 some odd years? 5.26 years, right? And what that population is, it's 48,421.053 people. Yeah. Yeah. You can't really say that. What's a .053 person? Very small, yeah, thanks. So I would round that off to the nearest person, right? 48,421, all right? So how would I state this answer? I would say that T is that, approximately, and that P is approximately 48,421. And there's units, it's peeps, okay? All right, any questions on how to find the intersection of two lines, either algebraically or graphically? All right, now this is really basic algebra. You've done this somewhere, haven't you? Is this new, really?
48,000
Is the population at that time 5.263 years? It's the same. It's a population for both towns at that time. Yeah, it's a common population. All righty, good, nice. What else can we say about this stuff? How are we doing on time? Okay. All right. Hopefully something that's obvious. Let me just briefly talk about this. What if I'm not graphing y equals mx plus b? Right? How do you graph that? You start at 5 on the y-axis and you count the slope up 2 over 1, because if it ain't a fraction, you can always put it over 1, right? But what if it's just this? What now? How do you graph that? That's what kind of line? Horizontal. Why? Because technically it's 0x. This is the same thing as saying 0x plus 5, so the slope is 0. If your delta y over delta x is 0, your y's are equal. When is a fraction 0? When the numerator is 0. When is the numerator 0? When the delta y is 0. When is the delta y 0? When the y2 equals y1. Horizontal. So the y's are always the same. The x's can be whatever they want. The y's are always 5. So it's still the same y-intercept, right? But how is this different? X equals 5. Or x equals any number. That's a vertical. We call that a no slope. We can't calculate the slope there, right? Because if you take a look at a vertical line, like x equals 5, say you take a look at this vertical line, when x equals 5. X is always 5, like 5 comma 10. X is always 5, like 5 comma negative 1. But what's the slope? What's 0? Delta y or delta x? Delta x. Now remember, the slope is delta y over delta x. If you're over 0, delta x is 0. That's undefined. Nobody knows how to divide by 0. Right? You know that a fraction is undefined if you're dividing by 0? Nobody knows how to divide by 0. So we call that a no slope or a vertical line. All right? So when y is alone equals a number, horizontal line. When x is alone equals a number, vertical line. When y is alone, horizontal line, 0 slope. When x is alone, vertical line, no slope. Right? Okay? And everyone knows what positive slope means. Positive slope means increasing. Negative slope means decreasing. 0 slope means horizontal, neither increasing nor decreasing, right? Hopefully you know this stuff. It's stuff that's in this section. I just want to make sure you know it. When are two lines parallel? What makes two lines parallel? If they have the same slope. Anytime two lines have the same slope, they're parallel. When are two lines perpendicular? Just inverse? Negative reciprocal slopes, right? So for example, if I go on to Ziggy, and I go, let me clear all this. Let's say if I want to graph y equals 5. It's hard to see why. It's not a good window. Look at this window. The values are humongous. I usually like to start with a zoom 4 if I can. But that's no good, but now because why? Because y max is 3.1. That's too small. That's not good enough. So how about zoom out a little bit? There it is. That's y equals 5. Okay. Now, what if I wanted to graph two lines with the same slope? That's a horizontal, in other words, right? How do I graph two lines with the same slope? Let's say y equals 2x plus 5. Did you expect that? It goes through 5 on the y-axis, right? As a positive slope. But what if I grab something else, like the same slope, but a different intercept? They're parallel. Do you see it? All right. What if I didn't do that? What if I did the negative reciprocal of the slope? What's the slope now on those graphs? 2 over 1. So the negative reciprocal, flip it, change the sign. What do you get? Negative 1/2. So let's do a slope of negative 1/2 plus whatever b you feel like. And this third line should be, when I graph it, what should it look like? Perpendicular to the other two. There you go. Okay? So any questions on horizontal, vertical, parallel, perpendicular? That's all that this section is about, aside from intersecting lines. Alrighty. So we'll go back if we have time to preview the homework. We'll take a look at that. Let's see. 1.6 is about linear regression or line fitting, which we did yesterday, right? Let's take a look at some examples of that. Let's see. This is section 1.6. Now we did a little bit of this yesterday. Remember we did linear regression? I had a scatter plot, and I had the calculator figure out the line of best fit. That's what this is. So whoever asked me yesterday, do we need to know this? Yes, we do. I think, who said that? Someone asked me, was it, you asked me yesterday, didn't you? Perla? Didn't you ask me yesterday, do we need to know this stuff with the statistics and the dots? Yeah, apparently we do. That's what this section is, okay? All right, let's practice that up. Linear regression. How do you find the line that best fits a scatter plot of points or data, right? You know what? How about, maybe we should just go straight to the homework page for this. All right, the homework page for this in 1.6 starts on page 48. Take a look at number 9, let's say. Now you have, on page 49, you have the multiples of 5 tonight, right? Now remember, don't get stuck on any one section for more than, like, say, maybe 30 minutes. Don't get crazy. 5, 10, 15, 20, that's fine, okay? So here's number 9, sort of like number 10 or number 5. It says, an ecologist tracks 290 zebra that were born in the year 2000. The number of zebras Z living each subsequent year is recorded in the table given, 1.37. Make a scatter plot where t equals 0 is 2000. All right, so if you're on page, the top of page 49, do you see table 1.37? You should have a book. Okay. Some people order the book online and you have an electronic version. You can log in, maybe? I don't know. Anyway, so here's the data. I'm gonna put this straight into the calculator, okay? So let's go to, let's quit this. I'm on the home screen. Let's clear this. Actually, let's clear all of this too. Okay, let's quit this. Now the first thing you gotta do is make sure you, what? That means you set up something weird in your L1, L2 probably. Did you do L1, L2 stuff yesterday? Yeah. Then that would mean that stat edit, these didn't line up? No, they don't. All right, how about this? Let's turn off stat plot for now. Yeah, stat plot messes you up. All right, but we're going to do a new stat plot now anyway, so. All right, so here we go. So the first thing you do is turn on stat plot if it's on already, right? So second, y equals, let's take plot 1, turn it on, and I'm going to use a dot scatter plot. I'm going to use L1, L2, and the squares. Now, you don't have to use L1 and L2. Some people, I noticed yesterday in the stat edit, didn't have L1, L2. Someone deleted L2 or something. So use L1, L3. I don't care. It doesn't matter. But make sure it says it here, L1, L3 then, right? So if you need to change it, go here. And do second 3 for L3. What? Very carefully. But I'm going to keep it to L2, so second L2. How do I get to that? All right, so this is what you do. Second is the yellow key. Second, and then y equals. You tell me, you asked me how to get to here. Then hit enter, and you get this. Hit enter, right. Now hit enter, or hit 1, and you get this, right? Now what do you got? L1, L2, yeah, that's it, perfect. That's it. That's exactly what I have, right? That's right. And so let's just make sure it's on. Make sure that, you hit enter on the on, okay? All right, now, go to stat. Nobody remembers? How do I enter the data? Count. No, not count. Edit, just edit, okay. Now, if you got stuff here, go to the top, hit clear, hit enter, go over to L2, go to the top, hit clear, hit enter. So you start with nothing. All right, now here's the data on the top right-hand side of page 49, table 1.37, right? It says year 2000, make it 0. So I'm going to do 0, 1, 2, 3, 4, 5, 6, 7, 8. 0, enter, 1, enter, 2, enter, 3. So we're making L1 the independent variable, the input, the t's, or the x's, right? 4, enter, 5, enter, 6, enter, 7, enter, and it goes up to 2008, and I started with 2000, which was 0. So boom. So 9 years, right? If you start at 0, you go to 8, that's 9 years, right? Do we have 9 pieces of data here? Yes, we do. All right, so how many zebra do we have in 2000? We have 290. Then we have 288, so it's decreasing. Then we have 206. Whoops, we had a famine. Then we're down to 140. Whoops, there was a drought. Then we had 90. Whoops, whatever they eat died. Then it's wow, this is not good. 64, 44, and I guess we're like endangered now. God, whoops, I messed up. What I messed up? What I mess up? I messed up. It's not lining up. 0, 1, 2, 3, 4, 5, 6, 7, 8. What? I missed 268. How could I miss that? There was so many zebras then. Dang it. Okay, 268. Enter. 206. Enter. 140. Enter. 90. Enter. 64. Enter. 44. Enter. And 8. Now, how do you get the calculator to find a good window for you when you're doing stats? So you don't have to worry about X min, X max, Y min, Y max. It does it for you automatically. So it fits all this data. Zoom 9. Or zoom stat, right? Boom. All right, so does that look linear to you? Does it look like a line would hit all the points or damn close to all the points? Not really. But I think they want you to come up with a linear regression, the line of best fit. What the line of best fit is, it's a line that goes through some of the points at least, right? Such that the points that are above and the points that are below are sort of equidistant from each other. So they sort of cancel the overestimates and the underestimates, so they cancel each other out. And how that's done, take statistics class. The calculator does it for you. Don't worry about that. All right. So, part A, make a scatter plot. We did. Part B, draw by eye a line of good fit and estimate that equation. Oh, okay. Could we do that? Can I draw in here? Give me a pen. Can I draw in this thing? No. It's not giving me an ink layer. All right. How would you draw a line so that there's basically as many points above the line as below the line? I'm thinking it probably goes through these 2 points right here. Can you imagine a line that goes through the point 0, 290, and what was the fourth one? 3, 206? Right? So, yeah, 2000 I made 0. I made x or t equal to 0. So couldn't you write the equation on that line? Let's see. The equation of the line that goes through, wait, I need another page. This is page 49. Number 9. I'm going to pretend that the line of best fit goes through the points 0 to 90 and 3, 206, I think was the other point. 3, 206. And so that's going to be my line of best fit by hand. It's not going to match necessarily what the calculator does. It does a better fit, but that's my eyeball fit. You might have a different fit. You might have a slightly different, but that's all right. Now, this is easy. You know how to do this. Do you know M or B already? You want to get Y equals MX plus B. Do you know M or B already? B is 2, no. 2000 is the year. B is 290, right? Because that's when you're on the Y-axis, when X is 0. And pretend this is X and Y, or or if you want T and P, T in years, P in population, or what Z. Z is a function of T, zebra, right? All right, now what are you missing then? You got to calculate what? The slope. All right, so let's do it. So the slope is, let's see, M is delta P, or delta Z if you want zebras, over delta T. So that's going to be 290 minus 206 over 0 minus 3. And 290 minus 206 is? Isn't it 84? Over what? Negative 3. And 3 goes into 84 nice and even, doesn't it? So it's going to be a negative what? 28? Okay. So there's your equation. Instead of y equals mx plus b, I'm going to say p equals negative 28t plus 290 is my line of best fit. It might not be the best fit because I'm just eyeballing it, right? So let's see what that looks like. Let's put that on the calculator. Alrighty. So go into y equals and put that in. Negative 28. I'm using function modes. So x plus 290. And it should go through those 2 points. There they go. Maybe I should have used the 4th point. Okay, but that's the idea. That's how you get your line of best fit by eyeballing it. All right, so that's part B. Part C, use a calculator or computer to find the equation of least squares. In other words, the linear regression on your calculator. How do you do that on your calculator again? Stat, calc, 4 or 8, yeah. And what if you wanted to type it in for you into Y1 or Y2? I got Y1 already, so I'll put it in Y2 for you. You gotta say second L1, comma, second L2, comma, then vars, then Y vars, then function. Now I'm not going to do Y1 because I got something there. Y2. Hit 2. And there it is. And I'm in float, so it doesn't have any round-off error. Remember we had a little round-off error yesterday when we didn't use floats, so leave it in float. So the slope, it's doing ax plus b instead of mx plus b. So a is the slope. Is negative 39 something? I estimated negative 28. Ugh. And the y-intercept for them was 314, and we made it 290. So ours wasn't that great. If you go into y equals, there it is. If you graph it, here's mine, here's my line, here's their line. It's such that the vertical distance between the points below and the points above, if you measure all those vertical distances, they cancel out. That's how you do a line of best fit. How to get y2? Go to vars. Go to y vars, right arrow. Go to 2. No, you didn't do it. No. Escape. Second quit. You got that? Okay. You got L1, L2. Okay. Vars. Right arrow to y vars. 1 for function. Or hit enter. And 2 for y2. Right. There you go. Enter that. Because I had something in Y1 I wanted to keep. I already wrote something in Y1. If you don't care about that or you want to write over it, that's fine. How do I do what? Okay. Right, that's the answer. Yeah, remember the R squared stuff? Yeah, I didn't save the state of my calculator. Okay, look. If you don't have R squared here, the coefficient of determination, I think it's called, you do this. Go to second, 0 is catalog. Go down to the D's. Look for diagnostic on. You have it already. You have the R squared. Diagnostic on, hit enter, enter. And then when you run it again, second enter, enter, it gives you the R squareds. And what that says is that it's hitting 96% of the time, it's hitting the points as a linear function. That it matches it 96% of the time. Where do I get vars from? Yeah, all right, let me start that from scratch. Stat, calc, 4. second 1, comma, second 2, comma, vars, right arrow, y vars, function, hit 1 or hit enter, and then I didn't want to write over what I had in y1, so I hit 2 for y2, and then hit enter. And now it gives me the correlation coefficient, which is r, 98% linear, and the coefficient of determination is 96%. Okay, so that was C. Interpret the slope and each intercept of the line. Interpret the correlation between the year and the number of terms. Okay. Huh? What?
That whole thing is the answer.
That whole thing is the answer. That's what you write down. But when you write it down on paper, you can round off to 3 places. So I would write negative 39.733x plus 314.667. Right? If I want to write the answer down, look, I'm going to write it down right now. So the calculator gives me a different answer. It gives me this. P equals negative 39733. P equals, now it's approximate, so I'm running off, right? So put a little dot there. Negative 3, dang it, I lost it already. 39.733, okay. 733, that's the slope, so mx, all right, plus the b, and the b was 314.267. 314.267. All right. Now, they're asking you to interpret the slope, negative 39. What does that mean? Negative 39, what does that mean? Roughly, negative 39 roughly. What does that mean? The slope. What are the units? Delta P over delta T. What's P? What are the units for P? Zebra, right? So we're losing 39 zebra per year. X is in years, right? Okay. What about the y-intercept, 314? Is that a real y-intercept? Wasn't the initial population 290? That 314 is a made-up number just to make the line fit. So that 314 is really not significant. The 290 is the initial population. The negative 39 is more akin to the slope of what we're really losing. But it's, remember, it was curvy. If I actually connected the dots, it was a curve. It wasn't a line, right? It's not really a line. It's close, but not quite. Also, this thing, it says interpret the R. What does it mean that R is negative 98%? It's good, it's near a line. It's near a line, but what about the negative? The correlation coefficient is negative whenever the function is decreasing. It matches the slope. Whenever the slope is negative, R is negative. Whenever the slope is positive, R is positive. So ahead of time you know if it's increasing or decreasing, right? Yeah. Nothing really. It's a made-up initial population to make the line have the right slope. So see, this 290 is the initial population. That's a good number to know. This negative 39-ish is a better estimate for your how much you're losing. So I like this B and I like this M. I don't like this B. My M wasn't good. I like this M. My B was good. I don't like this B. And that's what the question is saying. Interpret these numbers. Which one's good? I like this B. I like this M. And what does R mean? 98%, close to a line, negative, decreasing. Okay? There you go. All right, let's do some chapter 2 stuff. Oh my goodness. That's it for chapter 1. All right, so what's going on in chapter 2? Actually, I got ahead of myself. Chapter 2 is talking about points of intersection in 2.1. Oh no, wait, that's the skills refresher. Skip that. Skip that. Okay. All righty. All right, section 2.1 is about input and output. You're inputting X, you're outputting Y. Or you're inputting T in years and you're outputting P in zebras, right? Okay. It's more about what's function notation. We've been using function notation without saying so. So let's talk about this a little bit. All right? 2.1 says, what if G, your function G of X, is X squared plus 1 over 5 plus X. The question is, what is g of 3? What does that mean? First of all, g of 3 itself is like a y value. It's an output. How do you calculate the y value? What do you do with the 3? Plug it into the axis, right, okay. So 3 is an x value. G, or g of 3, is a y value, if you want to think of it that way. All right, so plug in 3. So you get, where am I? You get 3 squared plus 1 over 5 plus 3 is, well, what's the numerator? 10. It's 9 plus 1, right? 10 over 8. You can reduce that, right? Can't you reduce that by 2 to get 5/4? That's an improper fraction. Can you make it a mixed number? 1 and 1/4. Can you make it a decimal? 1.25. You should be able to, you should have the facility with fractions and decimals like that. Okay?
You can't just do that.
You can. But I don't do this. I don't do a lot of multiple choice questions on my test, but a lot of times did you guys take an entrance exam when you went into college? No? Didn't they have like a computerized exit exam and a whole bunch of multiple choice questions? Sometimes they'll give you the answers in terms like 5/4. Sometimes they'll give you the answers like 1 1/4. Sometimes they'll give you the answers as 1.25. You got to be able to change it up as needed, right? You just have to be able to recognize what that means. What would be g of -1, let's say? G of -1, what's that? What does that mean? Plug in -1 wherever you see x. But -1 squared is 1 plus the other one is 2 over 5 plus a -1. What's that going to be? 4, and 2/4 is really just 1/2 or 0.5. Okay. All right, so it's just function notation. All right. Remember the cricket problem? As the temperature increased, the rate of chirp increased too. All right. In the cricket problem, we had a function like this. Wait. Hang on. Did I do that? Yeah. Okay. We had T, the temperature in degrees Fahrenheit, was 1/4 of the chirp rate per minute plus 40. All right? So let's say we want to use that to figure out what the chirp rate is when T is 76. How do you figure that out? How do you find the chirp rate when the temperature is 76 degrees Fahrenheit? Plug in 76 where? Into T. All right, so if 76 is the temperature in Fahrenheit, degrees Fahrenheit, how do you find R? Isolate R, how? Subtract the 40, right? Okay, so you get 36 equals 1/4 of R. How do you get rid of the 1/4? Multiply with the reciprocal. That 1/4 is a fraction, right? So to get rid of it, it's multiplying. You divide. How do you divide by a fraction? Multiply with the reciprocal. Or cross multiply if you like. What is 4 times 36? 144. Okay. Just playing with functions, that's all this is. Okay. Here's another example. What if, are you okay with this? Any questions up here? Okay. We spent a little bit too long on chapter 1. I got to sort of breeze through chapter 2 a little bit, sorry. What if f of x is 1 over rad x minus 4? And you want to know, this is the question. Solve for x when f of x is 2. So how do you do that? How do you solve for x? You're plugging 2 in where? In place of f. F of x, or f is like y, okay? So I'm going to say 2, where am I? Equals 1 over rad x minus 4. How do you solve for x? Well, this is 2 over 1, isn't it? If you have one fraction equals another, you can cross multiply, so what do you get? 2 rad x minus 4 equals 1. Now, do you remember how to solve radical equations? You isolate the radical. You don't have to all the time, but usually that helps. So how do you get rid of the 2? Divide? Okay, so rad x minus 4 is what? 1/2. Now, how do you get rid of the radical? Square it. So x minus 4 is 1 over 1 squared is 1, 2 squared is 4. Okay. And then, what do you do last? Add the 4, and you get 4 1/4, or 4.25 if you like. Okay. What we're doing here is just getting used to function notation. If f of x equals 2, that means solve for x. If they give you f of 2, that means plug in 2 wherever you see x. Right? Get used to function notation. Okay, that's good. Let's see. All right. How about this? Let's go back to the chirping problem. Remember, t equals 1/4 r plus 40, right? Now, let's say you wanted to graph that. So you got to come up with a good window, right? Haven't we encountered this problem before? You got to have a good x-min, a good x-max, a good y-min, a good y-max. What that boils down to is, do you understand what the domain and range of this function are? What's the domain of a function? What you can plug in. In this case, we can plug in for r, right? R is like the x, right? And what's your range? What you get out, right? Now, you know that this is what kind of a function? It's linear, right? So what's the domain? What can you plug in? You can plug in anything, right? A line exists for all x, right? So I could say, if I said, let's do it this way. If I said y equals 1/4 x plus 40, I would say the domain is x is any number from, well, I can't say it that way, hang on. This is how it's usually said. X is in the domain of all real numbers. Do you know this notation? That weird e is a Greek lowercase epsilon, lowercase e in Greek, meaning element of the set of real numbers. Have you ever seen that notation? No? You could write it this way too. X is anything between negative infinity and positive infinity. Have you seen this kind of notation? Yeah? Or you could say x is in the interval, open interval, from negative infinity to positive infinity. Have you seen that notation? All these three notations mean the same thing. That's the domain. Those are the x values if y equals 1/4 x plus 40. But that's not the domain of the chirp function. Is it? Can you plug in any number for r? Does that make sense? What doesn't make sense? Here, x, I can plug in anything because it's a line defined for all x. But r, I can't plug in everything because it's a freaking cricket. Right? So what r values don't make sense? Negative chirp rates, right? What the hell does it mean, negative 40 chirps per minute? I don't know. Does that mean the cricket implodes? I don't know. What does that mean? Nothing. So what's the domain now? I would say r is what? Greater than 0. Now, can it go to infinity? Do you know any cricket that chirps infinitely many times per minute? No. There's got to be an upper limit somewhere. I don't know. I don't know. Who's into biology? Anybody know? What's the maximum chirp rate for a cricket? I don't know. Whatever. There's some max, right? Okay, I'm going to pretend I know. I'm going to make it up. Ready? I'm going to say, instead of this, I'm going to make it up. I'm going to say that r is between 0, could be 0. Remember, this is a function of temperature. The chirp rate changes with the temperature. What if the cricket is like frozen solid? No chirping, right? So could be. No, do you see what I'm talking about? You got to be careful. Is it a closed interval or an open interval? Can you allow 0, or does it have to be more than 0? Can I put this equal sign here? Like here, I have a less than symbol because I can't actually be negative infinity. That's not a number. But here I have an equal sign because not only is 0 a number, 0 is an allowable chirp rate. It's possible that cricket is dead, I guess. I don't know. Right? Okay. This is important. And all right, make it up. What's the maximum chirp rate? How much? 40,000. 40,000? What crickets are you hanging out with? 40. I think, well, when we looked at the data, I think it went up to like 200-ish somewhere. I don't know, I'm making this up. Let's say it has to be less than 300. Now let me make this a semi-closed interval. What does that mean? Semi-closed. R is between 0 and 300. But it includes 0 and not 300, because as soon as the chirp rate becomes 300, the bug explodes. Doesn't happen. Let's say. I don't know. Let's say that's true, right? Do you see what I'm saying here? You can define your domain as an open interval or a semi-closed interval. That's semi-closed, it starts closed. You can make it totally closed. This is totally closed. It includes the 300. All right, do you know this notation? You can have closed, you can have open, you can have semi-closed, you can have semi-open. You can open, you can have closed, you can have semi-closed, you can have semi-open. Right? There's 4 possibilities. Okay. So that's the domain of the chirp thing. What's the range? Well, think of it. Look at y equals 1 quarter x plus 40. It starts at 40 in the y-axis and it's up 1 over 4, up 1 over 4, right? So you can plug in any x you want, but what y's are you getting? There's the line. It goes up that way and it goes down that way. What y values are you getting? All real numbers, anything you want. It can go to negative infinity, it can go to positive infinity, right? It's going like this. It doesn't stop anywhere. It doesn't have a horizontal asymptote where it slows down or anything. All right, so I'm going to say that for y, the range is the same. Negative infinity to positive infinity. But does that make sense in the context of it's not y, it's T, the temperature? Right? What do you think the range is for T? The range for y is all real numbers. That's fine if you draw the whole line, right? But that's not a cricket. For a cricket, what do you think the temperature range is? Well, like I said, it stops chirping when it's frozen. So 32 degrees Fahrenheit, right? So there you go. All right, so let's say that T, where am I? T is between 32 degrees Fahrenheit and what do you think 300 chirps per minute relates to? How many degrees? Make up something. I don't have the data. 128. Okay, fine. 128 degrees. After which the bug melts or something. I don't know. Okay? Right? Now, is this an open interval? Is this a closed interval? Is this a semi-closed or semi-open? Are you going to allow 32 degrees? If I allow 0 chirps, I think I'm going to allow 32 degrees. Am I going to allow 128 degrees? If I'm not allowing 300? Well, actually, I allowed it, didn't I? I closed it. But say I don't. Say I don't close it. Let's say you can get up to 300, damn close to 300, but not 300. And let's say that 128 represents the 300. So I'm going to keep it open, right? All right, so there's a difference between the domain and the range of the function and the domain and the range of the real-world application that you're using that function to simulate, right? All right, so the x and the y, that's the domain and range of the line. But the r and the t, that's the domain and the range of the cricket, right? In the context of the real-world problem, you got to be careful. All right? That's what section 2.2 is about, interpreting domain and range. And what is domain and range? All right, so here's another example. A sunflower plant is measured every day, day t, and t is greater than or equal to 0. And what we're measuring is its height. How high does it grow? In centimeters, okay? And this is real-world data. A particular sunflower had this growth function or height function. I'm just jumping around. You don't need the page right now. I'm going to give you what you need. So what if h of t, h is the height of the sunflower plant in centimeters, and t is the number of days you're measuring, all right? Looks like this. 260 over 1 plus 24 times 0.9 to the t. The question here now is, what's the domain and the range? Now we're starting with t equals, what do you think? let t equal 0 be when you start the experiment. You're measuring the height of this thing. All right. So the domain of this function for t is 0 to stuff. Okay. 0 to what? Until you finish the experiment. 10 days, 20 days, 100 days, whatever, right? What if t? What if you didn't know what t represented? What's the domain of this function? Are there any t values you cannot plug in? No, because the only restriction you have here is that this is a fraction. This is a rational expression, right? And fractions are undefined. We talked about this. Fractions are undefined only when the denominator is 0. Is there any t value you can plug in that makes that denominator 0? No. So the domain is all real numbers. You can plug in any t you want, as far as the function is concerned. But as far as the experiment is concerned, what's your domain for t? 0 when you start, and 14 when you stop or something. Let's say you do this for 14 days. I don't know, right? So there's a domain for the function, there's a domain for the problem. It's different. What about the range? What are the h's going to be? Well, let's start. What if you plug in t equals 0? What's 0.9 to the 0? 1. What's 1 times 24? 24 plus the other one, 25. What's 260 divided by 25? 7. Did you say 7? 10 point something, right? All right, so the initial height is 10 point something centimeters. And now what happens to the height as you plug in bigger and bigger values of t? What if, remember, we started with 0.9 to the 0 is 1, right? What's 0.9 to the 1? 0.9. What's 0.9 to the 2? 0.81. Isn't that getting smaller? 0.9 to the 0 was 1. 0.9 to the 1 is 0.9. 0.9 to the 2 is 0.81. That number is getting smaller and smaller and smaller. When we multiply it by 24, we're not going to get 24 plus 1 is 25 anymore. We're going to get less than 24 plus 1 is less than 25. And smaller and smaller and smaller. So the 260 is being divided by smaller and smaller numbers. So the height starts at 10.4 something? And then what happens to the height? It's increasing. All right, let's graph this. Take a look at this on Ziggy. All right, let's graph this as a function. Let's see what the domain and the range of this function are, and then what the domain and the range of the problem are. So go to y equals, clear this, and if you don't want a stat plot, you can turn it off. Second, y equals 4, enter, and you're done. So y equals. Now, 260. Now be careful. How do I enter this? 260 divided by, you need parentheses, because if you don't do parentheses here, it'll divide by 1 and then add. Not divide by the whole thing. So I need parentheses around a complicated denominator. 1 plus 24 times 0.9 to the, and I'm in function mode, so I'm going to use x. All right, so, and close the denominator. There it is. Now if I do a zoom 4, I don't see nothing because the initial height you told me was, the initial height? 10 something, right? So my y max of 3.1 is not good enough. So window. Let's make the y max. By the way, you're going to have negative. Are you going to have negative time? X is the time. Are you going to have negative time? We're starting the experiment at 0. All right, let's do this as a function. Don't worry about the time. But how high does it go? All right, well, it starts at 10 something and it goes up, right? So let's make it, I don't know, 20. Let's see how high it goes. All right, so now you tell me, what's the domain and the range of the function? Forget about the sunflowers for a minute. What t values can you plug in? Was it ever undefined when we plugged in any t value? So you can plug in anything, all real numbers, negative infinity to positive infinity. What's the range? What are the range that you're getting? Well, it's not obvious from this graph, is it? All right, let's put in some more times. How about instead of negative 4.7 days to positive 4.7 days, how about negative 10 days to positive 10 days? How about that? And again, it's not days because I'm talking about the function, not the sunflower. Oh, well, now it goes over 20, doesn't it? It goes higher. It gets taller than 20, huh? All right, so window, how high do you think we're going to go? I'll give you a hint. It doesn't go to infinity. I'm at 20 already, so how high do you want to go? 50? All right, 50. it's not obvious what the range is, but I don't think it goes to infinity. I don't think this one goes from negative infinity to positive infinity. Let's take a look at some more of this. How about negative 100 to positive 100? How about a tick mark of 10? And let's make this symmetric. How about negative 50 to 50 in 10? Just to make it symmetric. And here we go. It's going way over 50. Wow. Okay, window. Let's make it negative, I don't know, 500 to positive 500. How about that? In tick marks of 100. You see what's going on? It looks like it's growing exponentially at first. Right? It's doing that concave up thing that we were talking about, exponential growth. But then it starts to decay. It's sort of like an exponential decay to a horizontal asymptote. There's a limiting height here. And that's what you got to figure out. So what's the range? The domain is all real numbers, right? At the t's. The h's, it's not all real numbers. It goes down to, let's see, trace it. Let's see how low it goes. Now at t equals 0, it starts at 10.4. But let's go to negative t's. How low does it go? 0.9, 0.7, 0.2, 0.1, 0.0, 0.02, 0.01, 0.004. What do you think the limit is, the lower limit? I think it's going to 0. So y equals 0, the horizontal line y equals 0, is a horizontal asymptote. Have you heard that word? Asymptote? It doesn't go below that line. How high does it go? Well, let's trace it the other way. Come on. 0.005, 0.03, 0.07, 0.2, 0.4, 0.9, 1.2, 2.4, 8, 10, 20.4, 50, 100, 200. How high is this going? 158? Yeah. I don't know if that's good enough. Quit this. On the home screen, let's plug in some values. Vars, y vars, function 1 of 10 days, of 100 days, of 1,000 days. What's going on? Of 10,000 days. The values are getting bigger and bigger and bigger, approximating. Notice it didn't change between 1,000 and 10,000 days. That's the upper limit. Have you heard this word limit? Have you heard this word asymptote? So there's a horizontal asymptote y equals 0 and a horizontal asymptote y equals 260. That's your range. No matter whether you're talking about sunflowers or not, that function is stuck between 0 and 260, right? All right, so this is what I'm going to say. The domain t is all real numbers from negative infinity to positive infinity. And the range for h is between 0 and 260. But notice, it grows asymptotically. It doesn't hit the line y equals 0. It never becomes 0. This is not a closed interval on the left side. And it approaches 260 asymptotically from below. It never really becomes 260. It gets damn close to 260. That's the limit. That's not the height. It gets close to 260, so I'm not going to close it. Yeah. That's a positive infinity. Yeah, I hate this pen. This pen is just not working out today. Negative infinity to positive infinity. Okay? I don't know if that's any better. All right, now, go back to the sunflower. What part of this graph actually describes the sunflower? What t values are valid for the sunflower? What h values are valid for the sunflower? Remember, we said we're going to start with t equals 0. So t has to be greater than 0 until you stop, I guess, whatever. So, but when t equals 0, what was the height? 10.4. But it still goes up to 260. So in terms of the context of the problem, where's my pointer? Okay. In terms of the context of the problem, I'm going to say that t is between 0, including 0, and whenever I stop the experiment, let's say 1,000 days. Okay? That's a closed interval. And h is between What and what? H is between, what was it at t equals 0? 10.4 centimeters, right? Centimeters. This is days. Day 0, day 1,000, right? Okay? This is centimeters. Okay? And then it actually doesn't hit 260, so I still have to keep this as an open interval here. So up to not quite 260, but damn close to 260 centimeters. So in the context of the problem, the piece of the graph that's stuck between 0 and 1,000 for t, and 10.4 and 260 for h, that's the sunflower. But this is the whole curve, if you want to talk about the whole function behavior. By the way, that weird shape where it's exponential growth and then exponential approaches an asymptote, that combination of those two kinds of curvature, that's called logistic growth. It's not exponential growth, it's logistic growth. All right, any questions how you interpret the domain and the range of function as opposed to the domain and the range of the problem that you're using the function to model? Yeah.
What did you do? You went to bars and then Y bars.
Oh, yeah, okay. Yeah, if you're on the home screen, if you do second mode is quit, you're on the home screen. There you're dealing with just a plain old scientific calculator, right? It's not a graphing calculator anymore. You can use your Y1 here, though. You could say vars, Y vars, function 1, and then in function notation, in parentheses, you can plug in whatever you want. Of day 1, of day 2, of day 3. This is function notation, f of x, day 5. Okay? So the sunflower was approximately 17 centimeters tall in 5 days of growth. Okay? The sunflower was approximately, let's say 10 days, approximately 27, almost 28 centimeters tall after 10 days of growth, or 10 days of the experiment, having started at 10.4 centimeters tall, right? So is everyone okay using function notation? That's what the vars are, they're functions. Y1 is a function, Y2 is a function, yeah. Yep. All right. Go to vars, the var key, you know where it is, right? Then you need your Nintendo key, go to the right to make this Y vars up here. Then I'm using functions, so hit enter or hit 1. And I want Y1 because I put the H into Y1. So I could hit 1 or I could hit enter. And then if you put in parentheses what you're plugging in for t, or plugging in for x, it's like 2 days, it's 12 centimeters tall, 12.7 centimeters tall, right? Or if I want 200 days, it's almost 260 tall. Huh? Whatever you've typed is stored. You can get it back by doing second enter. Second enter will give you the last one before that. Second enter will give you the last one before that. Second enter will give you the last one before that, and so forth. It's, what is that, a FIFO stack? Anyone know what I just said? FIFO? Anyone take computer science? Programming? No? FIFO, LIFOs? First in, first out. So the first in is the first out when you go backwards. Yeah. Wait, the last in is the first, no, it's LIFO. It's the last one that I typed is the first one that pops out when I back up. I'm sorry, say it? Into Y1, yep. 260 over parentheses, 1 plus 24 times 0.9 to the x. And I need to open close parentheses for the denominator, open close parentheses for the 0.9. Yeah. All right, so just playing around with function notation. That's what chapter 2 is about. Whether it's a linear function or not doesn't matter right now. Okay, anyone stuck? Okay. Yeah, because you didn't close the denominator. You need another parenthesis to close the denominator. By the way, the T83 is evil, and the 84. If you don't close parentheses where you're supposed to, it assumes somewhere to close it for you, and then you don't know where the hell it closed it, so that might be a problem. No, that's a weird graph. Oh, you still have stat plot on. I'm going to turn stat plot off. It's graphing your stat plot. Yeah, go to,
Turn that off.
yeah, second y equals plots off, enter. Now graph.
That
Well,
was
what's your,
all
what, yeah, wait, what's your window? Negative 100 to 100, negative 500 to 500. Still looking weird. There it goes. Your scale was weird. I changed the scale. When these numbers are very big, the scale can't be too small, or you're not going to see it. It just puts tick marks all over the x-axis or all over the y-axis. That's what they look weird. You had that, so I changed the scale. Otherwise, I just turned off your step line. But to turn off step line, if it's coming up, you do second y equals 4 enter. So you don't have to worry about what was in your step line. It'll just graph what's in your y1, and you're done. Okay. All right.
second y equals and then go to four.
Let's see it. Go to 4. Hit 4 and then enter. All right, and I did that for you already, but that's how you do it. Okay, 2.3 is about piecewise defined functions. Have you ever heard of piecewise defined functions? No? For different domains, it acts differently. For this domain, it might be a line. For this domain, it might be a different line. For this domain, it might be a parabola. For this domain, it might be an exponential growth. All right, let's see what that means. Let's say I define the following function. Let's talk about this. Let's say that f of x is x squared for certain x values and 6 minus x for certain other x values, okay? And I have to say what they are. So the domain where it acts like x squared is when x is less than or equal to 2. And the domain where it acts like 6 minus x is when x is greater than 2. Greater than 2. So this piecewise defined functions behaves differently depending on the input. X squared looks like a what? Do you know what y equals x squared looks like? A parabola, right? So it's parabolic when x is less than or equal to 2. And you know what 6 minus x looks like. Y equals 6 minus x is a line with a y-intercept of 6 and the slope of negative 1. Okay. So it's a piecewise defined function with 2 branches. You could have 3, 4, 5 branches, whatever. So how do you graph that by hand? Can you graph that by hand? Let's see. Let's see if we can graph that by hand. Here's your y-axis, here's your x-axis. Now y equals x squared goes through 0, 0 as a turning point. It goes like this, right? So for less, this is really bumpy here. All right, so for less than 2, let's say is here. Now if I plug in 2, what's x squared if I plug in 2? 4. So let's say this point is at x equals 2 and y equals 4. Now, how do you graph this? You're going to graph, notice what I'm saying is I'm only graphing this much of the parabola up to this closed point here because it says equal to 2 is allowed. Okay? If it wasn't equal to 2, I'd have an open circle. Now, what does 6 minus x look like? Well, it starts at 6, so that's 2, that's 4, that's 6. And it goes down 1 over 1, down 1 over 1. I think it goes through this point. But I'm not going to graph this piece of the line. Why? Because it's only for x is greater than 2 that I'm graphing the line. So when x is greater than 2 is here, this thing is getting so slippery. Move. It's sort of like that, let's say. I don't know if I have the right slope. It's sort of like that. All right? I think the slope is a little bit too steep, but that's what that function looks like. Okay? Now, some real-world phenomena work this way. For certain inputs, they act differently than for other inputs. So it's convenient to be able to deal with piecewise defined functions. How do you graph that on the calculator? Do you know how to do that on the calculator? Here we go. Divide by the domain because, all right, you've seen this before, right? Yeah. There's a lot of ways to do it. I do the dividing thing. Some people do it different. But here, this is what I'm going to do. I'm going to say, let y1 be this branch, let y2 be this branch, okay? I'm going to say x squared. Sometimes you need parentheses, sometimes you don't. I don't think you need them here, but I'm going to do play it safe. Parentheses x squared divided by parentheses the domain. Now the domain is x is less than or equal to 2. Where's the less than or equal to key? Do you know? Well, second math. Second math is test, and there's the less than or equal to key. It's 6. And less than or equal to 2. Now what this does is it introduces a Boolean. Oh God, it's computer science all day today. Nobody's taken computer science ever. No one's programmed in basic, Visual Basic, Java, right? Have you heard of the word Boolean? What does that mean? It's something that's true or false. Perfect. Okay. Now, in the graphing calculator is embedded a programming language called BASIC. It's a version of BASIC called TI Basic or TI-83 Basic. And in BASIC, Booleans resolve to true. True is a 1 and false is a 0. So what's happening? Whenever this is true, I'm dividing by 1. So what's x squared divided by 1? What's anything divided by 1? Itself. So it's going to graph x squared. But when x is less than or equal to 2 is false, this resolves to the number 0. And remember what happens when you divide by 0. It's undefined, so it won't graph. So there you go. Well, that's not a good window. Maybe, but how about Zoom 4? I did something wrong. Did I too? Oh, it's off the screen, is it? Wait, zoom out from the origin. Yeah, there it goes. See how it stops? So if you trace it, let's see where it stops. Does it stop at 2, 4? Yep, 2, and 2, 4 is part of the graph because we're allowing x equal to 2, so we're allowing y equal to 4. So that's the first part of the graph like we said here. Now how do you get this piece? You tell me. What will I type here? You know how to do this already. Parentheses, 6 minus x, close the parentheses, divided by, well, I need parentheses around the Boolean. So open parentheses, x is greater than 2. How do I get that? Second math is test, greater than is 3. 2, close it, graph it, and there you go. So that's how you graph a piecewise defined function on the calculator. So again, when x is greater than 2 is true, that turns into the number 1. And when you divide by 1, you're just going to graph 6 minus x. When this is false, this resolves to the number 0. When you divide by 0, it doesn't graph anything because it thinks it's an undefined function. Okay? So that's just a tricky way of graphing piecewise defined functions on your Ziggy. That's because change your window. Make sure your window, your Ymax includes high enough to see the 2, 4. You're not going to see that corner point, the 2, 4, unless Ymax is more than 4. Yeah, I started this. I did Zoom 4, which it's over here, right? So my Ymax isn't big enough. So I did a zoom out, but you could just make this bigger than 4. I don't know, 6. And you'll see it. There's the corner. The problem with, see, I like Zoom 4 because it's a square window. What's a square window? The aspect ratio is correct. A slope of 1 looks like a slope of 1. A circle looks like a circle. If you don't have the correct aspect ratio, if you have just some randomly chosen x min, x max, y min, y max without thinking about what you're doing, you might get a circle looking like it's squashed. You might see a slope of 1 looking like it's a slope of a quarter or something. So I like to start in the Zoom 4 because that's a correct aspect ratio. It makes a slope of 1 look like a 45-degree line. Because that's what slope of 1 does. It says 45 degrees with the x-axis. And circles look like circles and parabolas look like parabolas, right? And then if it's not big enough or small enough, I zoom in and zoom out. So it keeps the aspect ratio correct. But if you're not worried about that, you can just manipulate the x min, x max, y max the way you want. In this case, the problem was y max in Zoom 4. The y max wasn't big enough to see the corner, right? So if you go to y equals, right, the y max isn't big enough because the corner is at the point 2, 4. So simply, if you're not worried about a square window, to see the corner, simply make your y max big enough. Now it's squished, so the slopes don't look right, but you see the corner. So it's a complete graph. So you're always doing a trade-off, a game between, is it a complete graph, is it a square window? I like to have both when I can, but if I can't, I can't, whatever. All right, but that's a complete graph. It shows all the curvature of the parabola, the slope of the line, the corner. It shows all the intercepts. Well, actually, it doesn't show the x-intercept. Maybe I should make that a little bit bigger. The complete graph would show all the intercepts too, and that's a complete graph. It's not a square window, but it's a complete graph. So there's a trade-off between complete graph and square window. Sometimes you got to lose one to get the other. You got to play with it, right? All right, so that's what a piecewise defined function looks like. All right, here's another example of a piecewise defined function. Let's see. How about... Why don't we go to the homework page for 2.3? 2.3 homework page starts on page 83. So let's do an example like that. How about a question like, say, 14. Take a look at 14. You're doing 5, 10, 15, 20, right? So I'm not doing that one today. 14. The charge for a taxi ride in New York City is $2.50 upon entry and 40 cents for every 1/5 of a mile, rounded up to the nearest 1/5 of a mile, when the taxi cab is traveling for 6 miles per hour or more. In addition, New York State tax surcharge of 50 cents is added to the fare. Make a table showing the cost of the trip as a function of its length. Your table should start at 0 and go up to 2 miles in 1/5 mile intervals. Okay. Is this a piecewise defined function? Hang on. You know what? That's not a good example. I'm trying to find an example that's a piecewise defined function. That one isn't. Hang on. Trying to find one where you come up with your own piecewise defined function. Dang it, I'm trying to find a nice question. I'm not getting a good one here. That's not a good question. I don't like this homework set. It doesn't have decent questions. All right. All right, how about this? I'm going to make up something. How about this? Let's say you're making a phone call. Okay? And let's say you're making a long distance call. And it costs 99 cents for any call up to 20 minutes. Okay? But then there's an additional charge of 7 cents per minute after that. You see how that's a piecewise defined function? So up to 20 minutes, you pay 99 cents a minute. But after the 20 minutes, you're charged 7 cents more per minute above the 20. Okay, so it's not like it's 97 cents for every minute. It's 97 cents for everything over, right? So let's see, can we write a function for this? What is your cost function? Let's see. Here we go. What is your cost function as a function of t? It's got two branches. One is for when t is less than or equal to 20, and when t is more than 20 minutes, right? And I guess the assumption being that you can't do less than 0 minutes, okay? So how much does it cost to, okay, how much does it cost for the first 20 minutes? Like I said, it's a flat rate of 99 cents. So you write 0.99. Now, be careful. I'm not saying 0.99t. I'm saying it's 99 cents no matter what up to 20 minutes. You talk for 5 minutes, it's 99 cents. You talk for 12 minutes, it's 99 cents. You talk for 20 minutes, it's 99 cents. It's not a function of t, it's a constant. It's a horizontal line. Y equals 0.99, right? Okay, so that's what I'm saying. But now, what is it for over, whoops, I wrote this wrong, for over 20 minutes? What is that? Go away. Eraser, that's what I meant for over 20 minutes. What is it for over 20 minutes? And for every minute over 20 minutes, you get charged 7 cents extra. So you still got the 99, right? Plus 0.07 times, but not t. Why not? See, that's where it gets tricky. You're paying the 0.99 for the first 20 minutes, right? But then you're adding on $0.07, $0.07, 7 cents, not for every minute, for every minute over 20. So if you're talking for 25 minutes, this only counts for 5 of them. If you're talking for 28 minutes, this only counts for 8 of them. So it's t minus 20. There you go. Okay? That's what I'm saying. All right, so that's a typical example where piecewise defined functions come up. Now, you could simplify this. You could say, okay, c, where's my pointer? C is a function of time. It's a horizontal line or constant 0.99 cents for t between 20, and this is a semi-open interval, between 0 and 20. But, how do you simplify this? What do you do with the 0.07? Distribute, right? So 0.07 t minus, is it a point, what is it? Well, what is 20 times 0.07? 20 times 7 is 140, but that's 7 hundredths. So 140 divided by 100 is 1.4. So I'm going to say it's 99 plus 0.07 t minus 1.4? Okay, so it's 0.99 plus 0.07 t minus 1.4. But did I finish simplifying that? No, because they're like terms here. Who combines? 0.99 minus 1.4 is what? Negative 0.41, isn't it? Okay, so that's what I'm going to write. I'm going to say it's 0.07 t minus 0.41. Okay. Okay. All right, so how does this look? Can you graph this? Let's graph this on the calculator. Ready? Let's go. So let's put the calculator over here. All right, so y equals. All right, clear this, clear this. What should I write? For the first branch, right here. Now, 0.99, I don't think I need parentheses around it, but I'm just going to play it safe. Now, see, there's two things going on here. It's less than or equal to 20, but at the same time greater than 0. So I'm going to say divided by, parentheses, x is greater than 0, and divided by, parentheses, x is less than or equal to 20. Okay, so let's graph that. What happened? What's the domain of this function? The whole thing, both branches. What t-values are plugging in? I wrote this wrong, I'm sorry. For t greater than 20. This is between 0 and 20 and t greater than 20. Whoops, greater than 20. So what's the domain here? T has to be what? Greater than 0, right? This is saying up to 20 and this is saying over 20. But together it's anything over 0, right? So I need to see that. Okay. Go into your window. I don't care about x being negative. Make it 0. But I need to know what happens after 20 minutes. So how about, I don't know, let's make it 40 minutes. So it stops at 20, right? Boom. All right, good. Now what about this piece? This is a horizontal line. What's this? This should be a horizontal line. We got that, right? This should be a what? What shape? Another, what shape? Line, but not horizontal, is it? Right? It has a slope, right? A positive slope and a negative intercept. All right, so what do you type here? All right, so parentheses, 0.07. Again, in function mode, I got to use x instead of t. Minus 0.41. But I don't want to graph this for all x. I want to graph this only for t is greater than 20, right? So x, second math, greater than 20, close it. So it's going to graph that line, but starting there. Now, this is not necessarily a square window. That 0.07 slope may not look like that, but that's the graph. All right, so now how do you use this function? What if I asked you what's c of 10? What if I asked you what's c of 10? If I want to plug in 10, what does that mean? Am I plugging in the top branch or the lower branch? No, because that's for greater than 20. I want 10. So if I'm plugging in 10, I go here, and what is it? What's your cost for 10 minutes? 99 cents. It's a flat rate. Okay. What if I want C of 30? What do I want C of 30? Do I plug it into the first branch or the second branch? Is T equal to 30 allowed here? No. Is it allowed here? Yes. Plug it in there. All right, what's 30 times 0.07? 2.1. What's 2.1 minus 0.41? 4.69? Huh? 1.69, so $1.69? All right, let's see. If we go to the calculator and we trace it to 10, well, let me see if I can just second trace value at 10. I get the 0.99, right? But if I do second trace value at 30, what'd you say? 160. What happened? What happened? This is not an error. When it says that, it means it's undefined. Of course it's undefined. Because which y is it looking at? It's looking at what? y1. How do you get to y2? I'm trying to show you how to use the calculator, if you don't know already. Down arrow or up arrow. Boom. And is it 169, like you said? Amazing. I'm done. If you have any questions, stick around. Otherwise, we're done. Homework is section 1516, 21, 22, 23. Multiples of 5 in each exercise section. We'll go over that briefly tomorrow, finish chapter 2, and do chapter 3. All right, so have a nice day. We're done. Unless you have some questions, you can hang out. And that's all. All right, I got to go here.